Hello, welcome to the second video on the power sheet. I ran out of time in the last one, so I was only halfway through this one. So I wanted to finish talking about question 4b from the sheet. And let me see if I can pull up the question. Yeah, this one, 4b. So we were looking at how much chemical energy is converted by the motor during the lift if the efficiency is 20%. So we got to the point where we figured out that if 20% was 800 watts, which is what actually got converted into motion, that was the power output, then 100% would be 4000 watts. So that's what actually the machine would be consuming, the amount, and also converting from from chemical energy into other forms of energy. It's a diesel motor, so that's why they talk about chemical energy. It's burning diesel. Okay, it says it here, diesel motor. So since it's burning chemical energy, that's what it's converting into other things. So we said that the total was 400 watts. So that's how many joules per second it's consuming and converting. We know the seconds from the above question. You should have obtained 44 seconds. So if you multiply the total number of seconds by the joules per second, you will get the total amount of joules, which is what the question is trying to get you to answer. In part C, the diagram is unlabeled Sankey diagram for the process. Copy the diagram and label it, describe the lifting of the piano. There's only two ways the energy can go, and you should be able to do that, okay? Because that looks about 20 and 80% from the diagram. Question 5. The power of the electric motor of a locomotive unit pulling a train at a constant speed is 50 meters per second. So they give you a constant speed, so you can use your power is equal to force times velocity formula. They give you the power, which is 2.5 megawatts. Remember that mega is times 10 to the 6. What is the total resistance force on the train? So they're telling you. Question 5. You have a train and it's moving along with a velocity of 50 meters per second, and there is some resistance which you don't know, the force of resistance, and they tell you it's power of 2.5 times 10 to the 6 watts, which is 2.5 megawatts, and they ask you for the resistance. So this is a really easy question because they tell you it's going at a constant speed, and like once again, these are the super keyword, very important to see. If it's going at a constant speed, we know from F equals ma that the resultant has to be 0 if it's going at a constant speed, because there's no acceleration. Constant speed means no acceleration, so no resultant, so the two forces must be equal. In other words, if we find out the driving force, we know that the resistance force is the same. Okay, so let's find out the driving force. So the formula for power is equal to driving force times velocity, right? And the power is that, so we can get the driving force by saying that the power divided by the velocity, just by bringing the v down, dividing both sides by v. That means that the driving force is equal to the power, which is 2.5 times 10 to the 6. So 2.5 times 10 to the 6 divided by the velocity, which they give you in the question, is 50. That will give you the driving force. Once you know the driving force, you know that the resistance force is the same, because these are going at a constant speed. Question was easy enough. Question 6 is the power output of a windmill can be expressed as, so they give you the formula that you don't need to know, but they give it to you here for the power, where they need to tell you what the letters mean. So they say A is the area swept out by the windmill blades. Area. So if these are the blades, then the area would be the area. Rho is the density of air, so rho is density of the air, and v is the wind speed in case the dimension is constant. So that's wind speed and this is just a constant without any dimensions. Show that the units on both sides of the equation are the same. So we need to show that all of that bunch of stuff is the same as power. So let's see how we do this. So power is joules per second, right? And we said from before that joules was work done. So power is really work done per second. And work done, so here we're just dealing with the left hand side. Okay, so we can write it like this. Work time done over time. Now work is force times distance, so that's newtons times distance times meters divided by seconds, and newtons is F equals ma, so newtons is equal to kilograms, and A is meters per second squared, so that's 1 Newton, and we need to still multiply it by meters, and that divided by seconds. So the same as we did in the last video, we need to simplify this. We can't have -2 here and then divide by seconds. We need to put this in minuses also, so it comes here as a -3. So, and meters times meters is squared, so we have then kilograms meters squared. Well, we've already used this and this and this. Now we need to combine these two, and that's done by putting s to the -3. So that's a work, and we've already divided it by time. So that's the base units of the left hand side. So now our task is to show that these guys on the right hand side are the same. So let's see what's happening with the right hand side. K doesn't have any units because the question says it's dimensionless constant. So we can forget about K. What's A? Well, A is area, so that's going to be meters squared. Rho is density. Then the formula for density you should know is mass divided by volume. Right, the higher the mass of something, the bigger the density for the same constant volume. And so that's going to be in kilograms per meter cubed from the volume. So you can put it as minus there with the meters cubed. So what have we done so far? We've done area and density. We're missing now velocity cubed. So velocity cubed is going to be, what's velocity? Meters per second. Meters second to the -1. But since it's cubed, we need meters cubed seconds to the -3. Right? Because meters second to the -1 to the power of 3 is the same thing as meters cubed seconds to the -3. We multiply the indices. Here you can't see it, but there's actually a 1 there. So multiply the indices. Different than if you do this. If you do x squared times x squared, then you add the indices. But when you have one power and then to the power of another, then you multiply. And here you add. So we're nearly done here now. So what do we have? Well, we used everything. We just used the velocity cube. So now let's see if this simplifies to the same thing. What do we have here? Meters to the -3 times meters cubed. So the same way that I said here, when you multiply terms like that with powers, you just add them. So meters cubed times meters to the -3, that's going to add to 3 plus -3, that's going to be 0. So the -3 and the +3, they go away, and you're left with meters squared kilograms seconds to the -3. That's a bit of a strange 3. And up here we had kilograms meters squared seconds to the -3. Perfect. So the order is different because the kilograms is before, but it doesn't really matter, right? 3 times 4 is the same thing as 4 times 3. So these two guys are exactly the same, and we proved that the right and the left hand side are the same. Okay, that was a little bit long, but just follow it through and make sure you use base units, and it should be. In the next part, they ask you to draw a graph to show how it varies, and they're basically they're asking you for the variation with power and velocity, and they ask you how power increases with speed. It's cut off from the picture, but it says sketch a graph to show how the power increases with wind speed as v rises from 0 to 15. So let's ignore, so basically we keep all the other variables constant, and so we say that the area is the same, the density of the air is the same, and k is the same. So that makes sense that this is all a constant. So really the formula is p is equal to a constant times v cubed. So that formula would be p is equal to some constant which incorporates the 3 k, a, and rho. times v cubed. So what does that look like? Well, it's the same thing as y is equal to some constant times x cubed, right? And what does a cube look like? Well, a linear one looks like that, a squared one looks like that, and a cube one looks like that, right? So for the first bit, it should well, when v is 0, power is 0, so it starts here. You know that much. If you make this here number 0, then the power would be also 0. So you know that it starts from here, and it should go up like this, and then like that, and then like that. Actually, when they go through 0, they go like this, and they come through here, and then they go like that. That's what it would look like. So except this wouldn't be here. Right? But this would be much more steep than a quadratic. Quadratic would be like that way, and this would start going really high up. Wouldn't get vertical, but it would go really high. Okay, hopefully that makes sense for the sheet, and yeah, continue with your revision, and I'll see you in the next video.